Welcome! Today, we'll be diving into an exciting problem from linked lists, problem number 1019, next greater node in linked list. This problem challenges us to identify the next greater value for each node in a linked list, which is a common task in coding interviews and a great way to strengthen your data structure skills. Let's get started. In this problem, you're given the head of a singly linked list, where each node contains an integer value. Your task is to determine, for each node, the value of the next greater node in the list. The next greater node is defined as the first node appearing after the current node that has a strictly larger value. If no such node exists, you'll assign a value of 0 for that position. The output should be an array where each element corresponds to the next greater node for each node in the linked list. For example, if the input is a linked list represented as 2, 1, 5, you'll process each node sequentially to determine its next greater node, or 0 if none exists. Let's look at an example to clarify. For the input linked list 2, 1, 5, the output will be 5, 5, 0. Here's why: the first node has a value of 2, and the next greater node is the third node with a value of 5. The second node in the list has a value of 1, and again, the next greater node is the third node with a value of 5. For the third node with a value of 5, there are no nodes after it with a greater value, so its output is 0. Similarly, for a slightly more complex input like 2, 7, 4, 3, 5, the output is 7, 0, 5, 5, 0. The reasoning follows the same process: evaluate each node, and look for the first greater node appearing after it in the sequence. To further explain, let's break down the example: 2, 7, 4, 3, 5. The first node with value 2 as the next greater node is the second node, which is 7. The second node with value 7 doesn't have any greater node after it, so its output is 0. The third node with value 4 has the fifth node with value 5 as its next greater node. Similarly, the fourth node with value 3 also points to the fifth node with value 5 as its next greater node. Finally, the fifth node with value 5 has no greater node after it, so its output is 0. Now consider a broader example such as 1, 7, 5, 1, 9, 2, 5, 1. For the first node with value 1, the next greater node is the second node with value 7. For the second node with value 7, the next greater node is the fifth node with value 9. For the third node with value 5, the next greater node is again the fifth node, which is 9. Continuing the explanation for 1, 7, 5, 1, 9, 2, 5, 1, let's examine the remaining nodes. The fourth node with value 1 has the fifth node with value 9 as its next greater node. The fifth node with value 9 has no greater node after it, so its output is 0. The sixth node with value 2 has the seventh node with value 5 as its next greater node. The seventh node with value 5 has no greater node after it, so its output is 0. Finally, the eighth node with value 1 also has no greater node after it, so its output is 0. These examples help illustrate how you navigate through the list to identify the next greater node for each position. Now, let's also discuss the constraints and some special cases you might encounter while solving this problem. The constraints specify that the number of nodes in the linked list can range from 1 to 10,000, and each node's value lies between 1 and 1 billion. This means the solution needs to handle large inputs efficiently. For edge cases, consider a linked list with only one node. Since there are no other nodes, the output will always be 0. For a strictly increasing list, like 1, 2, 3, 4, the output will simply be the next node's value, with the last node being 0. In contrast, for a strictly decreasing list, like 4, 3, 2, 1, every node will have an output of 0 because no greater nodes exist for any position. Finally, with duplicate values, such as 2, 2, 3, the output should correctly reflect that the last node with value 3 is the next greater node for both instances of 2, resulting in 3, 3, 0. To tackle the problem of finding the next greater node in a linked list, we start by considering the brute force approach. The intuition behind this method is straightforward. For each node in the linked list, we traverse all subsequent nodes to look for the first one with a greater value. If such a value exists, we store it, otherwise, we record a 0. The steps are simple: begin with the first node, iterate through the list, and perform this search for each node. While this method aligns closely with the problem's definition, it has significant drawbacks. Specifically, the nested iterations result in a time complexity of n squared, which makes it highly inefficient as the size of the linked list grows. Additionally, while the space usage for storing results is linear, the time inefficiency becomes a bottleneck for large inputs. This motivates the need for a more optimized approach to improve performance. Now, moving to an optimized strategy, we use a monotonic decreasing stack to solve the problem efficiently. The key insight here is that the next greater node for any given node is simply the first node with a higher value that appears later in the list. By leveraging a monotonic stack, we can determine this efficiently. First, we convert the linked list into an array, which allows easier access to indices. Then, we use the stack to track the indices of nodes for which we haven't yet identified the next greater value. As we traverse the array, if the current value is greater than the value at the index stored on top of the stack, we update the result for that index and pop it from the stack. This process continues until the stack is empty or the current value is no longer greater. Finally, any indices left in the stack correspond to nodes that have no greater value, so their results are set to 0. This approach ensures that each node is pushed and popped from the stack at most once, giving us an overall time complexity of n. The space requirement remains n as well, but this includes both the result array and the stack, making it far more efficient than the brute force method. The monotonic stack approach is ultimately chosen because it strikes the perfect balance between efficiency and simplicity. While the brute force method is easy to understand, its n squared time complexity makes it impractical for larger inputs. In contrast, the stack-based approach processes the list in a single pass, achieving n time complexity. Converting the linked list into an array simplifies index management and allows the stack to operate efficiently. Of course, this conversion does require n extra space, but this trade-off is justified by the significant performance gains. One of the key insights here is recognizing that this problem is analogous to the well-known next greater element problem for arrays, enabling us to adapt the monotonic stack technique seamlessly. While the concept of a monotonic stack might initially feel less intuitive, its elegance and performance benefits make it the ideal solution for this problem. This approach avoids the pitfalls of nested iterations and offers a clear and scalable method to handle even the largest inputs effectively. In this problem, we need to find the next greater node for each node in a singly linked list. Each node contains an integer value, and for every node, we determine the next node in the list that has a greater value. If no such node exists, we simply return 0 for that node. The simplest approach to solve this is the brute force method. Here, for each node in the list, we traverse the remaining portion of the list to look for a node with a greater value. While this directly follows the problem's definition, it's computationally expensive because it requires revisiting nodes multiple times, leading to inefficiency for larger lists. To implement the brute force approach, we start by initializing a result array with zeros, where each position corresponds to a node in the linked list. This array will store the next greater values. Then, we use a nested loop structure. The outer loop iterates through each node using a pointer, while the inner loop checks the nodes that follow the current node. For each pair, we compare their values. If a greater value is found, we store it in the result array and break out of the inner loop to move on to the next node. After processing all nodes, the result array is returned. However, this method has a time complexity of n squared, because, for each node, we may traverse the remaining nodes in the list, making it highly inefficient for long lists. To address this inefficiency, we can use an optimized approach involving a monotonic stack. The optimized approach revolves around the use of a monotonic stack and an array representation of the linked list. First, we convert the linked list to an array, as this allows us to efficiently access nodes by their indices. We then initialize an empty stack to store indices and a result array filled with zeros. As we iterate through the array, we check the stack. If the current node's value is greater than the value at the index stored at the top of the stack, we pop the stack and update the result array for the corresponding index with the current value. This ensures each node is processed at most twice, once when it's pushed and once when it's popped, making the time complexity n. After processing all nodes, any remaining indices in the stack correspond to nodes without a next greater value, so their result values remain 0. Finally, we return the result array. The key to the optimized solution lies in the monotonic stack. This stack is used to maintain decreasing values, ensuring that when a greater value is encountered, it can immediately be matched to all smaller values in the stack. This eliminates the need for redundant traversals, making the algorithm much more efficient compared to the brute force method. Some important observations include handling edge cases, such as lists where all nodes have the same value or are strictly decreasing. Both cases result in a result array filled with zeros. For a single node list, the result is simply 0. Additionally, converting the linked list to an array is a crucial step, as it simplifies index-based operations, making it easier to implement the stack-based approach. Together with the result array, these data structures work in harmony to achieve an efficient solution. Let's walk through an example to see the optimized approach in action. Consider the input linked list 2, 1, 5. First, we convert it into an array 2, 1, 5 and initialize the result array as 0, 0, 0. We then start traversing the array. At index 0, the value is 2. Since the stack is empty, we push the index 0 onto the stack. At index 1, the value is 1. The stack currently contains 0. Because 1 is not greater than 2, we push index 1 onto the stack. At index 2, the value is 5. Now, 5 is greater than the value at index 1, so we pop index 1 from the stack and set result 1 to 5. Similarly, 5 is greater than the value at index 0, so we pop index 0 and set result 0 to 5. Finally, we push index 2 onto the stack. After processing, the stack holds indices of nodes without a next greater value, which remain as 0 in the result array. The final result is 5, 5, 0. This code solves the LeetCode problem number 1019 next greater node in linked list using an efficient approach with a monotonic stack. Let's break it down step by step. 1. Convert linked list to array. Since it's easier to work with arrays for indexing, we first traverse the linked list and store its values in a list called values. This transformation ensures that we can process the elements sequentially and access them directly by their index. 2. Initialize the result array. We create a result array of the same length as values, initialized to all zeros. This array will store the next greater node values for each position. If no greater value exists, the corresponding position remains 0. 3. Monotonic decreasing stack. The key to solving this problem efficiently is using a stack to keep track of indices of elements in a decreasing order. For each value in the values array. While the stack is not empty and the current value is greater than the value at the index stored at the top of the stack, we pop the stack and update the result for that index with the current value. Push the current index onto the stack for future comparisons. 4. Return the result. After traversing the array, the result array contains the next greater node values for every node in the linked list. This algorithm is efficient, with a time complexity of O(n), where n is the number of nodes in the linked list. The stack operations ensure that each element is processed at most twice, once when it's pushed onto the stack and once when it's popped. This makes the approach highly optimized compared to a brute force solution. To solve the next greater node in linked list problem, we start by defining a basic structure for our linked list using the listNode class. This includes constructors to handle both default and specific values, as well as linking nodes together. In the solution class, the next larger nodes method begins by converting the linked list into an array. We achieve this by iterating through the linked list, appending each node's value to a dynamic list called values. This transformation simplifies our problem, as we can now work with an indexed array instead of navigating through a linked list. Next, we initialize an integer array called result, where each element is set to 0. This array will hold the next greater values for each node, and its size matches the number of elements in the values list. We then use a monotonic decreasing stack to efficiently find the next greater elements. As we iterate through the values list, we compare the current value with the value at the index stored in the stack's top. If the current value is greater, we pop the stack, set the corresponding index in the result array to the current value, and continue until the condition no longer holds. Finally, we push the current index onto the stack to handle future comparisons. At the end of the loop, any indices still in the stack will naturally map to 0 in the result array, as there are no greater elements for them. The method then returns the filled result array. We start with the linked list 2, 1, 5. The first step is to convert this linked list into an array. By traversing the linked list node by node, we store the values in an array called values, which becomes 2, 1, 5. Next, we initialize a result array of the same size as values, filled with zeros, so result is 0, 0, 0. This will hold our final answers. To determine the next greater nodes, we use a monotonic decreasing stack. The stack is initialized as empty, and we iterate over the values array by index. In the first iteration, where the index is 0 and the current value is 2, the stack is empty, so we push the index 0 onto the stack. Now, the stack becomes 0. Moving to the second iteration with index 1 and value 1, we see that the top of the stack corresponds to the value 2, which is greater than the current value 1. Since no greater value is found, we push index 1 onto the stack, making it 0, 1. In the third iteration, with index 2 and value 5, we compare it with the top of the stack, which corresponds to value 1. Since 5 is greater than 1, we update result 1 to 5 and pop the stack, leaving it as 0. We then compare 5 with the next top of the stack, which corresponds to value 2. Since 5 is also greater than 2, we update result 0 to 5 and pop the stack again, leaving it empty. Finally, we push index 2 onto the stack, resulting in 2. After completing the iteration, the stack contains indices of elements that do not have a next greater node. These entries remain as 0 in the result array. For this example, the final result is 5, 5, 0, indicating that the next greater nodes for 2 and 1 are both 5, while 5 has no next greater node. Now, let's consider another example with the linked list 1, 7, 5, 3, 6, 4. Converting this linked list to an array gives us values as 1, 7, 5, 3, 6, 4. We initialize the result array as 0, 0, 0, 0, 0, 0, which is the same size as values. Using the monotonic decreasing stack, we start iterating. In the first iteration, with index 0 and value 1, the stack is empty, so we push index 0 onto the stack, making it 0. In the second iteration, with index 1 and value 7, we compare it to the top of the stack, which corresponds to value 1. Since 7 is greater than 1, we update result 0 to 7 and pop the stack, leaving it empty. Then, we push index 1 onto the stack, resulting in 1. In the third iteration, with index 2 and value 5, the stack remains unchanged because the top of the stack corresponds to value 7, which is greater than 5. We simply push index 2 onto the stack, making it 1, 2. Similarly, in the fourth iteration, with index 3 and value 3, the top of the stack is 5, which is greater than 3. So, we push index 3 onto the stack, resulting in 1, 2, 3. In the fifth iteration, with index 4 and value 6, we compare it with the top of the stack, which corresponds to value 3. Since 6 is greater than 3, we update result 3 to 6 and pop the stack, leaving it as 1, 2. We then compare 6 with the next top of the stack, which corresponds to value 5. Since 6 is greater than 5, we update result 2 to 6 and pop the stack again, leaving it as 1. Finally, we push index 4 onto the stack, making it 1, 4. In the sixth iteration, with index 5 and value 4, the top of the stack is 6, which is greater than 4, so we simply push index 5 onto the stack, resulting in 1, 4, 5. At the end of the iteration, the stack contains indices of elements that have no next greater node. These remain as 0 in the result array. For this example, the final result is 7, 0, 6, 6, 0, 0, meaning the next greater nodes for 1, 5, and 3 are 7, 6, and 6 respectively, while 7, 6, and 4 have no next greater node. Finally, consider the linked list 5, 4, 3, 2, 1. Converting this to an array gives values as 5, 4, 3, 2, 1. We initialize the result array as 0, 0, 0, 0, 0. Using the monotonic decreasing stack, we start iterating. In the first iteration, with index 0 and value 5, the stack is empty, so we push index 0 onto the stack, making it 0. In the second iteration, with index 1 and value 4, the top of the stack corresponds to value 5, which is greater than 4, so we push index 1 onto the stack, making it 0, 1. Similarly, in the third iteration, with index 2 and value 3, the top of the stack corresponds to value 4, which is greater than 3, so we push index 2 onto the stack, resulting in 0, 1, 2. In the fourth iteration, with index 3 and value 2, the top of the stack corresponds to value 3, which is greater than 2, so we push index 3 onto the stack, making it 0, 1, 2, 3. Finally, in the fifth iteration, with index 4 and value 1, the top of the stack corresponds to value 2, which is greater than 1, so we push index 4 onto the stack, resulting in 0, 1, 2, 3, 4. At the end of the iteration, the stack contains all indices because no element in the list has a next greater node. As a result, the result array remains unchanged as 0, 0, 0, 0, 0. This indicates that none of the nodes in the linked list has a next greater node, which is expected given that the list is in strictly decreasing order. The time complexity of our solution is O, n, where n is the length of the linked list. To understand this, let's break it into two main operations. First, we convert the linked list into an array. Here, the while loop traverses the entire list once, visiting each node exactly one time. This traversal takes O, n, time. Then, we process the array using a monotonic stack. The for loop iterates through the array, which has n elements, so the outer loop runs O, n, times. Inside this loop, there's a while loop that pops elements from the stack whenever the current value is greater than the value at the index stored at the top of the stack. Importantly, each index is pushed onto the stack once and popped at most once, so the total time for all push and pop operations across the array is O, n. Combining the traversal of the linked list and the processing of the array, the total time complexity is O, n, plus O, n, which simplifies to O, n. Now let's analyze the space complexity, which is also O, n. This comes from three main components. First, there's the array we use to store the values of the linked list. This array requires O, n, space because there are n nodes in the list. Second, we initialize a result array to store the next greater values, and this result array is the same size as the values array, contributing another O, n, space. Finally, the monotonic stack stores the indices of the values array. In the worst case, when the array is monotonically decreasing, all n indices will be stored in the stack simultaneously, adding another O, n, space. When we add up the space used by the values array, the result array, and the stack, the total space complexity is O, n, plus O, n, plus O, n, which simplifies to O, n. To put this into perspective, let's compare the optimized approach with a brute force approach. In a brute force solution, we would compare each element of the linked list with every subsequent element to find the next greater node. This involves a nested loop, where each of the n elements performs up to n comparisons, leading to an O, n squared, time complexity. The optimized approach, on the other hand, uses a monotonic stack to track indices efficiently. By processing each element at most twice, once during a push and once during a pop, we reduce the time complexity to O, n. While the space complexity remains O, n, in both approaches due to the storage of linked list elements and indices, the optimized approach offers significant improvements in runtime. Breaking it down further, in the best case, where the values array is sorted in increasing order, each index is pushed and popped immediately, resulting in linear processing. For average cases, with random arrangements of values, each index is still processed at most twice, maintaining O, n. Even in the worst case, where the array is sorted in decreasing order, the stack holds all indices until the end, but the time complexity still remains O, n. Finally, let's provide a mathematical justification for why the overall time complexity is O, n. In our optimized approach, each index is pushed onto the stack exactly once and popped at most once. This means the total number of stack operations, including both pushes and pops, is bounded by 2n. If we denote the constant factor for each operation as c, the total stack operations can be expressed as c asterisk 2n, which is O, n. Additionally, traversing the linked list to construct the array is another O, n, operation. When we combine all these steps, the traversal, the array construction, and the stack processing, the total time complexity remains O, n, confirming the efficiency of this approach. When solving this problem, there are a few common mistakes to watch out for. First, some may confuse the next greater requirement with the largest value in the list. This happens when you search for the maximum value across the entire list, rather than focusing on finding the very next node with a greater value. Remember, the goal is to identify the immediate next greater node, not the largest overall. Second, an inefficient brute force implementation is another pitfall. Repeatedly traversing the list for every node results in an O(n)² time complexity, which becomes computationally expensive for larger inputs. Instead, optimize your approach using techniques like stacks, monotonic structures, or reverse traversal to achieve O(n) efficiency. Lastly, edge cases are often neglected. For instance, in a strictly decreasing list or when dealing with a single node list, there may not always be a next greater node. Make sure to handle such cases explicitly by returning a default value like -1 or none. Another mistake to avoid is modifying the linked list directly while trying to determine the next greater node. Changing node pointers or data during traversal can corrupt the list structure and produce incorrect results. It's better to use auxiliary data structures, such as a stack or an array, to store intermediate states. Additionally, incorrect stack usage in optimized approaches can lead to subtle errors. For example, if you pop values from the stack prematurely or fail to maintain proper tracking of indices, you might miss comparisons or end up with the wrong results. To address this, ensure that your stack operations are carefully designed and the logic for managing indices and values is robust. In interviews, this problem is often presented as a variation of the next greater element family of problems. Recognizing this pattern early can help you leverage optimized techniques like monotonic stacks. A key focus should be on achieving O(n) solutions, as brute force methods with O(n)² complexity are too slow for competitive scenarios. It's also important to consider edge cases, such as empty lists, single node lists, or lists with duplicates, and ask clarifying questions to ensure you understand how to handle them. Additionally, discussing trade-offs is a valuable strategy in interviews. For instance, you could compare the simplicity of the brute force approach with the efficiency of optimized solutions, demonstrating your ability to assess different methods based on the problem's constraints. Several related problems can help you build a deeper understanding of this topic. For example, LeetCode 739, Daily Temperatures, uses a similar monotonic stack approach to find the next greater temperature for each day. LeetCode 503, Next Greater Element 2, introduces a circular array variation of the problem, while LeetCode 496, Next Greater Element I, presents a simpler version involving two arrays. Of course, LeetCode 1019, Next Greater Node in Linked List, is the exact problem we are discussing here and is frequently asked in interviews. When considering alternative approaches, the brute force method involves comparing each node with all subsequent nodes. While this is straightforward to implement, it has an O(n)² complexity, making it impractical for large inputs. However, it can work well for small-sized lists where scalability is less of a concern. A more efficient approach is to use a monotonic stack. Here, you process nodes in reverse order, maintaining a stack to track indices or values in decreasing order. This ensures that each node is processed only once, achieving an O(n) time complexity. Although this method is highly efficient, it can be more complex to implement compared to brute force. Another alternative is reverse traversal. By traversing the list in reverse, you can keep track of the maximum value encountered so far and determine the next greater node efficiently. This approach also runs in O(n) time but may require reversing the list or using recursion. If recursion is used, it can be memory intensive, so you'll need to weigh these considerations carefully. Both of these approaches highlight the trade-offs between implementation complexity and performance efficiency. Great job completing this problem. In summary, we explored both brute force and optimized approaches, ultimately implementing an efficient stack-based solution with O(n) time complexity. We also discussed key takeaways like the power of monotonic stacks and optimization strategies for linked lists. Thanks again for watching. Be sure to like, comment, and subscribe for more coding content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!